Have you ever wondered what makes up the world around us? At the most fundamental level, the answer lies in atoms and molecules. These tiny particles, far too small to see with the naked eye, are the building blocks of everything we see, touch, and even breathe. Imagine a giant Lego set. Atoms are like the individual Lego bricks. Just like you can combine Legos in countless ways to build complex structures, atoms combine to form everything from the air we breathe to the water we drink. Molecules, on the other hand, are like those pre-designed Lego sets. They are formed when two or more atoms join together in a specific arrangement. Take water, for example. A single water molecule is made up of two hydrogen atoms and one oxygen atom, hence the chemical formula H2O. Now imagine billions upon billions of these water molecules sticking together. That's what makes up a single drop of water. Understanding atoms and molecules is like unlocking a secret code to the universe. It allows us to comprehend the properties of matter, how different substances interact, and even the very basis of life itself. So, buckle up, dear readers, as we embark on a thrilling journey into the minuscule world of atoms and molecules. Their interactions and combinations create the incredible diversity of materials and substances we encounter every day. The idea of atoms has been around for a surprisingly long time. Way back in ancient India, a philosopher named Maharishi Kanad proposed that matter was made up of indivisible particles called anu. Meanwhile, over in ancient Greece, a philosopher named Democritus came up with a similar idea. He called these indivisible particles atomos, which means uncuttable in Greek. Democritus imagined atoms as tiny, solid spheres, each with a different shape and size depending on the substance they made up. These early thinkers were remarkably prescient, but their ideas were largely philosophical. It wasn't until centuries later that the scientific study of atoms truly began. Fast forward to the 18th century, when chemistry as a science began to blossom. Scientists were busy experimenting with different substances, trying to understand how they combined and reacted. From these experiments emerged some fundamental laws that hinted at the existence of atoms. One of these laws was the law of conservation of mass, which states that in a closed system, the total mass of the reactants before a chemical reaction must equal the total mass of the products after the reaction. In simpler terms, matter cannot be created or destroyed, only transformed. Another crucial law was the law of constant proportions, put forth by French chemist Joseph Proust. This law states that a chemical compound always contains the same elements in the same proportions by mass, regardless of the source or method of preparation. These laws provided strong evidence that matter was made up of discrete units combining in specific ratios. Enter John Dalton, an English chemist, and his groundbreaking atomic theory in the early 19th century. Section 4. Unraveling the atom structure and size. Dalton's atomic theory was a game-changer. He proposed that all matter is composed of tiny, indivisible particles called atoms. He also postulated that atoms of a given element are identical in mass and properties, while atoms of different elements have different masses and properties. Furthermore, he stated that atoms combine in simple, whole number ratios to form chemical compounds, echoing the law of constant proportions. Now, we know that atoms aren't actually indivisible. They are made up of even smaller particles called protons, neutrons, and electrons. But Dalton's theory was a crucial step in the right direction. But just how small are atoms? The answer is very, very small. They are so small that we measure them in nanometers, which are 1/1,000,000th of a meter. To put that in perspective, a human hair is about 80,000 nanometers wide. An atom is roughly 0.1 to 0.5 nanometers in diameter. Section 5. From atoms to molecules, a chemical bond. Now let's talk about molecules. Remember those Lego sets we talked about earlier? Molecules are formed when two or more atoms stick together. This sticking together is due to chemical bonds, which are forces of attraction that hold atoms together. There are different types of chemical bonds, but the basic idea is that atoms want to be stable, and they achieve stability by sharing or transferring electrons with other atoms. Molecules can be made up of the same type of atom like oxygen gas, which we breathe, or different types of atoms like carbon dioxide, which we exhale. When a molecule is made up of two or more different types of atoms, we call it a compound. Sometimes one atom might have a stronger pull on the shared electrons than the other atoms. This can create ions, which are atoms or groups of atoms that carry an electrical charge. These opposite charges are what cause ionic bonds, like the bond between sodium and chloride ions in table salt. Section 6. Measuring the microscopic moles and calculations. So, we've talked about atoms and molecules, but how do we measure something so infinitesimally small, especially when dealing with billions upon billions of them? This is where the concept of the mole comes in handy. The mole is a fundamental unit of measurement in chemistry. It's simply a very, very large number, 6.022 times 10 to the power of 23. This number is called Avogadro's number, named after Italian scientist Amedeo Avogadro. Just like a dozen represents 12, a mole represents 6.022 times 10 to the power of 23 entities, whether they're atoms, molecules, or even donuts. Using the mole allows us to relate the microscopic world of atoms and molecules to the macroscopic world we experience. For example, 1 mole of carbon-12 atoms has a mass of exactly 12 grams. This mass is called the atomic mass, and it's different for each element. We can use atomic masses to calculate the molecular mass of a compound, which is the sum of the atomic masses of all the atoms in a molecule. Understanding the mole concept is crucial for performing chemical calculations, like determining the amount of reactants needed for a reaction or the amount of product expected. From the earliest philosophical musings to the sophisticated scientific models of today, our understanding of atoms and molecules has come a long way.